function, some curve, and we know there's a zillion functions and curves we could have. So given any function and starting at some value and ending at some value, how could we find the length of the curve? So we should have the general up here. No. So we'll call this function f. And we want the the length of the arc from A to B. And this could be any function, right? This could be crazy exponential or sinusoidal function or something, or some combination thereof. Could be anything, right? So we want to just have a formula for finding this length, like you have the formula for the length around a circle. So what will the general gist of this be? How can we use things we've learned so far this semester, or just general idea? What's the general idea we're going to use to get the length of that arc right there?
Can we split it up into segments?
Split it up into segments and then do what? Right. Yeah, so it's going to be, we want to take a zillion little pieces of the arc, get each one, and then add them all up. And then that's the principle of what? Integral, right? So the length is going to be the sum of a zillion little lengths, right? So what are we going to do? We're going to break this up like this. And so to get an approximation for this length of curve right here, we want a straight line, right? Straight line. Because that we can get. So we'll do a straight line there. Straight line there, like that. Okay, so we're going to use straight lines connecting points on the curve to approximate little lengths of the curve. And those straight lines we're going to call delta S. So delta S1, delta S2, delta S3, etc. So we're going to start, before we get to this, we're going to start with approximate, right? So the approximate curve length from A to B is going to be the sum say as J. So say we end up with n of these, right? So say we end up with n of these segments. So we're going to let J go from 1 to n, and we're going to add up all of them. So the first one, the second one, the third one, all the way up to the nth. So J is keeping track of which segment we're on, right? First segment, second segment, third segment. And then S sub J is the length, or delta S sub J is the little length of each segment. And we're going to sum all them up, starting with the first one up to the last one, the nth. So n total segments, right? N. That's a B. Okay, so how are we going to get that length? How are we going to get that length? It's the same as summing up what? by doing a line segment, that was supposed to have made it easy, right? The length of a segment should be easy. So how do we calculate the length of, say, that first little segment? What's that? Is the slope the same as the length? We want the length of it. Distance formula. What's the distance formula? Where does the distance formula come from? No? What about a triangle? Yeah, so there's a triangle here. So that delta S1, that's the hypotenuse, right? So how do we write the length of the hypotenuse of a triangle? Right. That's what Haley was saying too. Right. It's a Pythagorean theorem, right? It's going to be the square root of this squared plus this squared. Well, what is this? From this point to this point, what is that line segment right there, that base of the triangle? Delta x, the change in x, right? And the height is delta y. So it's going to be the square root of delta xj squared plus I like this derivation because everything should make sense. There's no real parts to it where it's like, oh, it's so confusing, I don't get it. Everything should make sense. Every one of those little delta s's is the hypotenuse of a right triangle formed by the corresponding delta x and delta y as the two legs. You see that? So it's going to be the sum of the square roots of the legs, and the legs are delta x squared, the legs squared. So delta xj squared plus delta yj squared. We're going to sum all those up, and that's the same as summing up all the... Okay, so then the next thing is to... So we know eventually this is going to be an integral, right? It's going to be integral, and when we have our integrals, we want to have it in the form of what? Function times dx, right?
Yeah.
So thinking about that in the end, wanting integral of function times dx, we have to kind of extract delta x out of this thing. Okay, and so the way we can do that is this. Here's the trick to that. I'm going to multiply by delta x over delta x, but as the square root of delta x squared. So I'll just show you what it looks like. So I'm going to take this thing, I'm going to multiply it by delta x sub j. That's going to be my dx, but I can't just do that, right? I can only multiply by 1 and not change the value of something, right? So I'm going to really multiply by delta xj over delta xj, but this one in the bottom, I'm going to put it inside here eventually, so I'm going to do the square root of delta xj squared. So I've just multiplied by 1. You see that? I've just multiplied by delta xj over delta xj. But I've done it in such a way that this numerator will eventually be my dx, and the denominator will be square root, so I can now combine these square roots, combine these together. So what do I get?
You get square root of 1 plus, change of y or change of x.
Yeah.
Derivative squared, right?
Alvaro. Wow, okay, awesome. So we're going to put delta xj squared underneath here. So this thing is going to go underneath there, and it's going to go underneath there. So we're going to have, do you see that first term will be 1? And then the second term will be delta yj squared over delta xj squared, which is also delta yj over delta xj quantity squared. times delta xj. I kind of did 2 steps at once. Is it okay?
Yeah.
I moved it. It's under the square root, so I moved the delta xj squared underneath the square root with the first one. So then it becomes 1, and then delta yj over delta xj quantity squared. So now we're going to make things small. So now we're going to let the number of segments get really, really big, and the size of those segments really, really small. So we're going to have like a zillion teeny little line segments. So that's letting delta xj go to 0, or n get really big. Either way, same thing. So when we do that, what does the summation become? So now we're going to say we want a zillion of these little line segments from A to B. What does the summation become? Integral. So that becomes our integral. And it'll be from A to B. Right? And then we'll have square root of 1 plus something. Now, when delta x gets very, very small, what is delta yj over delta xj? When delta x gets very, very small. No. So what is that? Do we recognize what that is? For very, very small change in x. The change in y over the change in x. Even for not a small change in x, even for a big change in x, what is delta y over delta x? Rate of change, right? Rate of change. See, that's the rate of change. Or, I mean, if you're talking geometry, it's slope, but that's the rate of change, right? That's how fast y is changing with respect to x. So if x gets really, really small, and we think about all the x values from A to B as x is really, really small, what is that, essentially? How does it relate to function f? Yeah, it's a derivative, right? So the rate of change at any point x, when change in x is very, very small, that's our derivative function, right? That's our derivative function. So it's just f prime of x. So that is the okay, so for exam 2, you are responsible for this derivation. Knowing the meaning of every part, being able to reproduce any part of it or the whole thing. Okay, because this is very everything should make sense. So you wouldn't have known to do this step here, but I showed you why we do it and how it works. But everything here is very attainable, and so you're responsible for this for exam 2.
Can we just go over what J and N mean?
N is the total number of segments that we picked to start with. So in this example, 1, 2, 3, maybe I had 5 or something.
And then what is J?
Well, so we're summing up a bunch of these, right? So it's delta S1 plus delta S2 plus delta S3, is it right? All the way to delta Sn. That's what this means. Keep summing the same thing over and over and over again, right? So J is the index. J tells us what segment we're on. J starts at this is how summation works. J will start at 1 and we'll do this term. Then we let J be 2, and we do the next term. And then J is 3, and then we add them all up. Yeah, so that's how summation works. Other questions on it? Okay, but remember, this dx is part of the math. This was all based on this square root, this length of the hypotenuse, right? So this whole thing is still the length of a little hypotenuse. You need the dx. Just the square root is not the length of the hypotenuse. This is multiplication. This square root function times dx gives us a little length of the hypotenuse. So that's that same point we talked about before. It's not dx is not just an afterthought signifying integration. It's part of the math. Without it, you're summing up the wrong thing. Right? Without the dx there, you're not summing up a bunch of little line segments. I don't know what that is. It's something else, but it's not a bunch of little line segments. So length of one tiny hypotenuse includes the dx. Multiply. Yeah.
Do I know what the function represents?
It's just like, so this is more of a geometry situation. So whatever function you have in the plane, we're finding the length on that function from here to here. So it could be, if you want a real world situation, maybe a function models some boundary of some area region, like, I don't know.
So this function, the square root of 1 plus fx prime squared.
Yeah.
What the function?
I don't know what that means. What I know is that when you multiply it by dx, that's a little hypotenuse. That's what I know. That's what I'm saying. So when you divide the hypotenuse by dx, what the length of the hypotenuse by dx, what does that give you? I don't know. I don't really know how to conceive that. That's why I'm saying you need the whole product times dx, and then you have the length of a tiny hypotenuse. But just that function standing alone, I don't really have a meaning for that. That's a good question. Any more? So let's look at an example. Forgot to. X to the 3 halves from 0 to 1. And so we know that our length of our curve is from A to B, 1 plus derivative squared on the square root dx. So you'll have to know the derivation of this formula, understand it, where it comes from, all the meanings of it, but then you also know how to use it, right? So we're going to use it here to find whatever the length of this curve is from 0 to 1, 1 plus 6x to the 3 halves. So what are we going to do? How do we set this up? A is 0, B is 1, and now 1 plus what? So we're going to need what the derivative is. What is the derivative? 9x to the 1/2, is that right? Did I do the math right? So that's going to be the derivative, which is 9 square root of x squared. And so what is that? 1 plus 81x dx should be an easy antiderivative. Let's see, who can tell me what that antiderivative is? Daphne, can you tell me? Adrian, can you tell me? Take your time. Good. All right. Now we just got to clean up the mess, right? So what will we need out in front? So what are we going to need now? 1 over 81. Anything else? 2/3. Right? And then that from 0 to 1. Neither of which give us 0. Both are going to be terms in here. So we're going to have, and what is 240/3? Is that right? And I think you're going to get, what, 82 when you put 1 in? Minus? Thank you. And then when you put 0 in, you're going to just 1 to the 3 halves with just 1. So times whatever that is. Questions on this? Really easy example. Just using the formula. Anybody? Okay, so one thing you can use this for, and I kind of wanted to do this with volume, but we didn't have time, so we'll do it here, is we can actually use this, the arc length integral, to derive the basic formulas of like geometry curves. So like, let's derive the circumference of a circle. So we know the circumference of a circle is what? Well, and that's just because that's what they told us, right? Like you go to the back of the geometry book and it says C equals 2 pi r. So let's use this integral for arc length, and let's actually derive that that's the case, and show and prove that that is indeed the length of a circle. So we're gonna, what do we need? We need it. So where should we put our circle to make life the easiest? What's that? Yeah, make the center at 0. Okay. And we know we're going to need what? So if our length is integral from a to b of square root of 1 minus, say, y prime is it plus? Sorry. Yeah, thanks. Do I have it right now? Okay, so what are we going to need? Okay, and if we need y prime, what are we going to need to get y prime? Yeah, so exactly. We're going to need what is this thing? Y equals what? We need the function of the circle. So we need first. So we want this to be for any circle, right? So what will the coordinates of this point be? It's any circle. Any circle. Okay, but it's going to be a defined circle to start with, so we're going to R0, right? Where R is a constant, right? R is a constant, but it can be any constant. So given any circle, we can put it on the center, and then we know its radius is R. So our circle has radius R. So if that's the case, then what does Y equal if our radius is R? What's that? Equation of a circle is x squared plus equals r squared. R squared. So what does y equal?
Square root of r squared minus x squared.
And is that the circle? What's that? That's a point?
No, that's the y.
Is this the equation of the circle? Y equals square root of r squared minus x squared.
No,
When
the
it's kind of
equation of the
yours.
y point on the circle.
That's the equation for half of this.
Which half, Adrian? Good.
The first quadrant quarter, or the upper portion.
This is the top half of the circle. When you take the square root, what do you get? Plus or minus. So the minus is the bottom half. Okay? So this is just the top half. Just like we saw in those problems, those parabolas we had, or x, that was with y squared, right? If you change it around and put y as a function of x, you just get the top half. This top half. So we'll find the distance of the top half. What do we expect the length of the top half to be? Or even better yet, to make it really easy, let's do this quarter right here. And so how long should that be in the end? What do we expect if we use the arc length formula to find that length right there? What should it end up being? 1/4 of the circumference, right?
Yeah.
So we're expecting 1/4 of, what's the circumference? 2 pi r, which is?
Pi r over 2.
Okay, so this is our target. We're going to find this length right here, and it ought to be pi r over 2, and then we've essentially proved that the circumference is 2 pi r, right? So here we go. So this is, what's our limits of integration going to be? She wants from 0 to r. Agree with that? Yeah, from 0 to r. And we're going to have a square root of 1 plus what? Right, so we need the derivative of our circle function squared and dx. What is the derivative? 1/2 times this thing to the negative 1/2 times negative 2x. Did you catch it? Chain rule, right? Chain rule derivative. We need the derivative of our function, which our function is the circle. So we're going to do the chain rule, right? We're going to do 1/2 times that thing to the negative 1/2, and by the chain rule times negative 2x. Okay, so immediately we see that the minus this can go with this can go. And then we'll have x squared, and we'll have this thing squared, which makes that square root go away. So that's kind of nice. And the negative goes away, right? So the opposite of x squared is the same as x squared, right? Are we good? Okay so far?
Yeah.
All right, so now we want to add these two. We want to add these, make one big fraction out of this. Then we might have a fighting chance to get rid of the square root somewhere, right? But with the 1 plus something, this is locked in the square root. But if we can get a single fraction, this might allow us to apply the square root. Okay, so what's my common denominator? R squared minus x squared. So in the numerator, I'm going to have that 1 turns into what? R squared minus x squared, and then plus x squared. Okay. Does that help? Yeah, because now the numerator is? r squared under the square root, right? Okay, we're making progress. And now we've simplified this thing. We're going to start thinking about some way to get the antiderivative of this, right? To get an actual value, to get this value of this integral, we're going to have to get an antiderivative. So, does it? Do we have any ideas for? So, is it undoing the chain rule? What would we need for it to be undoing the chain rule? X in the numerator. If we had X in the numerator, we could undo the chain rule. Don't have it. Okay? So, what else do we got? Partial fractions. It's a square root. No good. Undoing products. Well, maybe, but it's certainly not one of the basic forms for undoing the product. So we can. So, do we recognize what this might be kind of like? Arc sine. Do you see this kind of like arc sine? What would we need to get to make it arc sine? It's got to be, arc sine is
1 minus x squared at the bottom.
got to have a 1 here. In order for this to be arc sine, this has got to be a 1. So what we'll do is we'll divide that by r squared. We'll divide that by r squared. So, but that's underneath the square root, right? So what did I really divide the bottom by? Yeah, I divided the bottom by radical r squared, which is what? Just r. So if I divide the top by r, I haven't changed the value of it. You see that? So I just divided the top and bottom by r. In the bottom, that was of the form radical r squared, or r squared under the square root. And now it looks like arc sine. So we got a nice cancellation there in the numerator. Look at that, 1. So it's going to square root of 1 minus. Did I lose you anywhere? Ask me. Are we good? Yeah. Now I've got it. What is that? We got the antiderivative. It is?
Arc sine of x over r.
Arc sine. So yeah, so this is x over r quantity squared. So this is arc sine of, okay, careful. Is that the actual antiderivative of this? No, not negative. It's a chain rule derivative. So we get it like,
Times r.
so what are we going to need so that we would get exactly this as the derivative? So I have multiply by r or divide by r? Multiply. From 0 to r. We're so close. So we have the r times the sine inverse of 1, right? Yuck. Oh, that's okay, right? Okay, and then minus r times the sine inverse of 0. So we're saying, what angle gives us a sine of 1?
Is that pi over 2?
He wants pi over 2. Does pi over 2 give a sine, a y coordinate of 1? And what angle gives a sine of 0? Did we get it? Pi r over 2, which is what? 1/4 of the length of the circle. So times 4 would be 2 pi r. We got it. That's what we were expecting, right? Pi r over 2. So we just used the arc length formula to derive or prove that the length of the circumference of a circle is 2 pi r by doing 1/4 of it, pi r over 2. Any questions? Okay, let's do some physics. Let's do some physics. Last chance. Questions? Can I erase? Okay, physics applications. So the first ones we're going to do have to do with force and work. This is a big part of these physics applications. The ideas of force and work. So let's just talk generally about these quantities or these properties in general. Okay, work. Work is the amount of force that you apply over a distance. So if I push this table, a couple feet, that's going to take some work, right? And to do that, I'm going to have to apply the force to the table for those couple of feet. So the force that I apply times the distance that I move it will be the total work that I do. What if I move this table, I push this table all the way to that wall? More or less work? More work because more distance, right? So I might be applying the same force the whole way, but for a much longer distance. So it's going to be more work, right? It's going to be more work to do that. Okay, so that's easy, but what if the force varies? So what if the carpet gradually gets more and more worn out, and so there's less and less friction as I go, right? So as I'm pushing, there's a lot of friction at the beginning, but then the carpet gets more and more worn out, and so it becomes slicker. And so now what happens to the force as I'm pushing? Push it. It's decreasing because there's less friction. So there's some force function now that I'm experiencing as I push this table to the wall. So the force is continually changing. So how am I going to calculate the total work if I have a continually varying amount of work that I'm using to push the table to the wall? How am I going to find the total amount of work? What's that? Do segments, right? So it's the same thing as before. So the total amount of work. So mathematically, how could we represent what the total amount of work would be? Total work would equal what? Of?
Whatever your function of the variation of force, so it's like rate of change of force, I guess.
But even more general than that, integral of just what? If we want the total amount of work, it's going to be the integral of?
Force.
Not the integral of force. Right. Little bits of work, right? Little bits of work. Total, it's going to be the integral of little bits of work. Just like the total amount of change was all the sum of the little bits of change, and the total area was the sum of the little areas, and the total volume was the sum of the little volumes. And what? The arc length was the sum of little lengths, right? So it's the same thing again. So we're gonna find a little bit of work. So if I make the distance small enough, I can assume a constant force for a little bit of distance. But then now the next little bit of distance will have a slightly different force. So it's the same principle we did before. We're going to find the typical amount of work and then sum them all up. Oops. So in order to do this, we're going to need to know some things about force and work. So let's go over some of the basics of that. So force, there's let's talk about metric versus English. What's going on with force here? So I'm sure you've all heard force equals mass times acceleration. Okay, this is used primarily with metric units. Okay, because with English units, mass is kind of obsolete. They don't really. We'll get to that. But this equation, force equals mass times acceleration, is primarily used when you're talking about metric units. Okay. So your mass is in grams or kilograms. Right? Mass is grams or kilograms. And A is the acceleration in meters per second squared. Again, metric units. And then when you take kilograms times meters per second squared, you get newtons. So kilograms times meters per second squared is force in the metric system, which is newtons. Okay, so weight is force. Weight is just the force of gravity on an object. So then when you're talking about weight force, you use, instead of A, use a specific value of A called G. So it's still F equals ma, but now we're talking about the acceleration of gravity. Okay, and so then in the metrics, that's 9.8 meters per second squared. So this is how things speed up when they fall. Every second, they go 9.8 meters per second faster than the previous second. The speed keeps increasing by 9.8 meters per second every second. Or in the English, 32.2 feet per second squared. So weight then in the metric system is measured in newtons. Why? Because it's a force, right? Weight is a force, and force in the metric system is newtons. So you measure weight in the metric system with newtons. Not what? What do we think it is?
Kilograms.
It's not kilograms. Kilograms is mass. That's apples and oranges. Kilograms is the amount of matter. It's how much stuff. It's not force. Weight is force, and so then we need newtons for weight. But it's hard to. Our whole world is based around the idea or thought that kilograms is weight, but it's not. Kilograms is mass, newtons is force, and so if you're measuring the weight of something in the metric system, that's in newtons. Okay? In the English system, of course, pounds. So this goes back to what I was talking about before. So, but in the English system, mass is usually not used. All force values and weights are given in pounds when you have a problem in the English system. So, when we have a problem in English units, we're not going to use F equals mg because we're not going to have the mass, so we don't multiply by g. We're going to have F. That's pounds, right? That force is the weight, and that's pounds. So whenever you come to these physics problems and it's in feet and pounds and miles in the English units, you're not going to use mg. You're not going to use mg because pounds you already have. Your F is pounds, right? Your F is pounds already. But when you come to a metric problem, they may start by giving you the mass in grams or kilograms, and then to get newtons, to get weight or force, you're going to use mg. This causes confusion. So I'm trying to alert you ahead of time. Does that make sense? Okay, questions on this slide? Okay, so if the force varies according to a function, we said the total work is the sum of little bits of work, or the sum of dW's, right? This is consistent with everything we've talked about so far this summer. That's what an integral is. Summing up a bunch of little changes to get the total change. All right, so let's talk about springs. With springs, here's the basic formula that characterizes a spring. F equals kx. So F is the force to hold the spring at a displacement of x. So you imagine if you just had a spring and you stretched it, well, now it's going to require force to keep it stretched. Or same thing, pushing it, right? So if the spring, you're pushing on the spring, it's going to require force to keep it pushed to that displacement. So that's what this F is referring to in this formula. K is a spring constant. So this is a constant for a given spring. So it's basically expressing the stiffness of the spring. So like a slinky has an extremely low spring constant. It requires very little force, right, to stretch it or to hold it stretched or to, all right. So who knows cars? So the spring in the wheels, is that the strut or the shock? Is that the strut? The shock, the spring part? So the shock in your car, high or low spring constant? Very high. Shock. Shock. So a car shock has a very high, right? Because to get that thing to budge a little bit, it requires a lot of force, right? And that's what you're experiencing in your car. Your car's so heavy, and it's bouncing on things. So the heaviness of the car, the movement of the car is applying a lot of force, so that those shocks are absorbing some of those bumps. That's very high spring constant. Most springs would be in between, right? Most springs would be something in between a slinky and a car shock. All right, and then X is not the total length of the spring. It's the displacement from the natural length. Okay, so this is important to understand these problems. So say this is the natural length of the spring. It's attached to a wall or something, okay? So I'm going to pull this spring out. So what is X? X is this distance. The displacement from its natural length. Displacement from the natural length of the spring. Make sense? So don't be confused. It's not, X is not from here to here. It's how much it got stretched from its at rest length. Okay, so let's do an example. So a force of 40 newtons is required to hold a spring that's been stretched from its natural length of 10 centimeters to 15 centimeters. How much work is done in stretching the spring from 15 to 18? So what happens when, so what does this say? This formula says that as you continue to stretch the spring, what happens to the force to hold it? Increases, right? The more that I displace it, the more force it's going to take. So if I'm stretching a spring, what's happening to that force to stretch it? Yeah, I mean, it's going to take more and more force to keep stretching it, right? So this is the same example that I told you with the table. Like to push the table, if the force is continually changing, then it's not just a simple, work isn't just force times distance, but that force is continually changing. Same thing with a spring. As I stretch it out here, X, the force is going to be low at first, but then it's going to get harder and harder and harder to pull this spring out. So that force of stretching it is going to increase as we go. So what I'm going to do? So what I need to do is think about somewhere along the way, just stretching it a little bit, and assuming the force is constant for that little bit of stretch. Then I can calculate a little bit of work, right? So I want a typical amount of work. So I want just like we did with the volumes and areas. So delta W is going to equal what? Yeah, force times a little bit of distance, right? So it's going to be the force times the little bit of distance that I pull it. Because for a little bit of distance, I can assume a constant force, right? For a little bit of distance of stretch, I can say, okay, the force will be constant for that little amount. But for a big amount of stretch, the force is continually changing, so I can't use. I've got to do it for a little bit. All right. So what is F? F is what? Kx, right? So my work is going to be Kx delta x. What is K for this spring? No, K is going to be in what? Newtons per meter. So we need to figure out what K is, right? When the force is 40, the displacement is? Right, this is a displacement of 5, right? So therefore K is?
8 newtons per centimeter, right?
Yeah, so it would be newtons per centimeter. So we can just do this problem in centimeters. Everything's given in centimeters, so we can just keep it in centimeters. So this spring constant is 8 newtons per centimeter. So then we have our little bit of work is going to be 8x delta x. So given a displacement of x, the little bit of work required to stretch it just a little bit further than x would be 8x delta x. So then what's the total work to stretch it from 15 to 18? What are we going to do? Sum up all the little bits of work. We're going to sum up all the little bits of work from 15 to 18. You guys agree with that? Of the little bit of work, right? Is that right?
Yeah.
Nope. Why not? Adrian's saying 5 to 8. What is x? What's the meaning of x? What's the meaning of x? Displacement from natural length. Displacement from natural length. So I want to stretch it from 15 to 18 centimeters. 5 to 8. Because this is x values, right? So it's displacements. What's the initial displacement if it starts at 15 centimeters? 5 is the initial displacement to a final displacement of 8. So that will give us the total work required for this problem. Okay, questions on that problem? Okay, let's do this one. So a 20 kilogram chain hangs 30 meters from the roof over the side of a tall building. How much work is required to pull the entire chain up to the roof? Okay, so so can we just do straight up force times distance? Will it work? I mean, can we find so what is force in this problem? Force is really, what are we talking about? When we're talking about force in this problem? Weight, right? Force, so we're talking about the weight. So can we just find the weight of the chain? What's the weight of the chain? mg, right? 20 times 9.8. Is that 196? No. 196?
Yeah.
So if that's the force, and then the distance times, can I do 196 times 30? Does that give me the total work? If not, why not? He said as you pull more of the chain onto the roof, the weight is less. So with every link of chain that you get onto the roof, the weight of what you have to pull remaining is less. So that force is continually decreasing as you're pulling the chain up onto the roof. So this doesn't work. You can't just do the total force. That would be the work just to lift the whole chain 30 meters, right? If you're just lifting that whole chain 30 meters into the air, like from a starting point to an ending point, yes, then it would be the 196 times 30. But in this scenario, as you get chain onto the roof, you have less weight and so less force to pull the remaining chain. Okay, so what are we going to do? We're going to do a typical a bit of work. Which is going to be delta W is going to equal what? Same thing as before. Force times. So if we move the chain anywhere along the way, if we move the chain just a little bit, we can just assume a constant force. However much chain is hanging over the building gives us an amount of force, and we're just gonna pull it up a little bit. We'll just assume that force stays the same for that little change in distance, just like we did for the spring. Okay, so say that this is. So say that this was 30 meters. So just faster. Say that the building itself is 30 meters, and I've already pulled some up here. So this is X amount of chain remaining. Okay. So X is amount of chain, or length of chain remaining hanging over the building. Okay, length of chain hanging over the edge. And so here, and it started the whole length of the building, and so here I am at some point, and only X remains. So what is the force? The force is the weight of X meters of chain. So how much does X meters of chain weigh? What's that? So if 20 kilograms weighs 30 meters, how many kilograms per meter is that? 2/3 kilograms per meter. And if I have X meters, how many kilograms is that? I have X meters of chain, right? So 2/3 X is the kilograms. And so now what's the weight then? The weight is M times G. Did you catch it? I went fast. Basically, if 20 kilograms is 30 meters, then each meter weighs 2/3 of a kilogram. I have X meters hanging over, so therefore I have 2/3 times X kilograms. And so then the force or the weight of that amount of chain is 2/3 x, the mass times gravity, 9.8.
Why is it 2/3 x?
Because every meter is 2/3 of a kilogram, and I have x meters. Right? This says that every meter of chain is 2/3 kilograms. If 20 kilograms weighs 30 meters, then every meter is 2/3 of a kilogram, and I have x meters. Does that make sense? So now I get my little bit of work. My little bit of work is 2/3 x times 9.8 times the little bit of distance. And so now the total work is integral from 0 to 30. So I'm going to sum up all the little bits of work starting when x is 0. So even though I'm pulling this way, I'm still going to start from the little bit of work that when it was 0 all the way to when I had 30 meters of chain hanging over. I'm going to sum up all my little bits of work.
We do it after 30 because we included 30 in the ratio, right?
Because that's how much chain is hanging over, 30 meters, right? So
Oh, okay.
so it starts at 30, we pull the whole thing up, and then ends at 0. So when we integrate it, we kind of integrate it backwards. It's like the little bit of work at the very end plus the next little second to end. So I'm kind of integrating backwards from how you think about the way the problem is going. It doesn't matter what order you sum something up in, right? The sum is the same. So we're going to sum from 0 to 30. Questions on this example?
Sorry, if we integral from 30 to 0, are they the same?
Negative. So it'll be negative. You'll get a negative amount of work.
Why it's from 0 to 30? Because x is the length of the chain. So if we put over the chain, the length should be from 30 to 0.
Yeah, so if you do from 30 to 0, then you get a negative amount of work, which, so why? Yeah, it's a philosophical question for another day.
Why are we integrating from 0 to 30 and not?
It has to do with dx, because dx,
Better than I did.
yeah,
We didn't get to do the one with the sand.
what?
We didn't get to do the one with the sand. It was like sand.
We didn't get to it, yeah, so we'll do it tomorrow.
Alright.
This is why.
Started yesterday. Because dx is negative.
Dx is negative. Dx is in the opposite direction that the chain is moving. You see that? So
Yes.
if x is pointed down like this, then dx, a positive dx is lengthening the chain. So maybe then our typical amount of work is, does this make it better? If we do, so the typical amount of work is going to be times a little negative change in x, right? And then we can integrate from 30 to 0. What's that?
But you get the same.
What's that? And yeah.
So it's less complicated to do it with positive signs.
Yes.
I'm really good at science.
Okay, so I think I found the explanation. We're integrating from 0 to 30 because when we start pulling, we have pulled exactly.
No, when you start pulling, x is 30.
Yes.
And when you're done pulling, x is 0.
Why is it?
So that's why you would do, if you want to do it that way, if you want to say when you start pulling, there's length of x 30 hanging over, okay? When you're done pulling, there's 0 hanging over. So that would be integrating from 30 to 0. But if you do that, then dx is in the same positive direction as x is. Dx is this way. So your little bit of work is going to be the force of x times negative dx, because you're going to pull this way, you're not going to extend it down, you're going to pull it up in the opposite direction of positive dx. So then that would mean that you would do,
Yeah.
so that your change in x is negative x, and so then you're going to get the opposite, the work is the opposite of this, and so that's integrating from 30 to 0, the opposite of that. Is that better?
Yeah.
Does that make sense to you? When x is 30, that's where you start at. All the chain is hanging to the ground, and you're going to move it up a little bit for that much force.
Yes.
But moving it up is actually the opposite of dx, because we're defining x as the amount of chain hanging down. So then your dx is negative. So then you would have a negative delta x, which would make this thing negative, and you integrate it from 30 to 0. So if you want to make x go this way, so we could do a different thing. We could do this. We could say x is, so from the ground, x would be this way. Then dx would be like this, a little change up like this, right? And then your little bit of work would be blue. What would it be? This is more complicated. So now it would be 2/3 times 30 minus x times 9.8 times positive delta x. And now you would integrate from 0 to 30. So then it would be from 0 to 30, because you start when x is 0. You have all of it. And then at the end, x is 30. So it'd be x 0 to 30, 2/3, 30 minus x times 9.8 dx.
So they should get the same value.
Yeah, you'll get the same value.
That makes sense.
So I think it's easier, this is easier than trying to figure out that this x is the amount of what? It's how, x is basically how much chain you've pulled, right? X is how much chain you've pulled so far, right? So when you've pulled 0, you have a force of 30. When you've pulled all 30, you have a force of 0. So this x is now amount or length of chain pulled. And then you can integrate from 0 to 30. And it's just all positive, because your dx now is in the same direction as the change is in the actual same direction as x. Good?
Yeah. Thank you, sir.
You're welcome.
Tomorrow.
I'll be here, 10:30.